Imagine trying to catch a fly in a dark room. You can hear it buzzing around, but you can't see it clearly. You know it's there, somewhere, but its exact position is a mystery. You swing your hand, aiming for the buzzing sound. Each attempt is a guess, a shot in the dark, literally and figuratively. You might get close, but the fly always seems to be one step ahead. Sometimes you get close, but you never know exactly where the fly is. It's a game of probabilities where each swing is influenced by your last attempt and the fly's unpredictable movements. The act of trying to catch it changes its position. Your movements create air currents, altering the fly's path. It's a dynamic interaction where both you and the fly are constantly adapting. The harder you try to pin it down, the more elusive it becomes. This frustration is a perfect metaphor for the uncertainty we face in many aspects of life. This simple scenario illustrates a profound truth about our universe, a truth enshrined in Heisenberg's Uncertainty Principle. This principle states that there is a fundamental limit to what we can know about the properties of particles. Just like the fly in the dark, the subatomic particles that make up our world are inherently uncertain. They don't have definite positions or velocities until we measure them. The more precisely we try to measure one aspect of a particle, like its position, the less we can know about another aspect, like its momentum. This trade-off is not due to our lack of skill or technology, but a fundamental property of nature. This isn't just a limitation of our instruments or a reflection of our imperfect senses. It's a built-in feature of the universe, a reminder that some things are inherently unknowable. It's a fundamental feature of reality itself. This uncertainty is woven into the very fabric of the cosmos, affecting everything from the smallest particles to the largest structures. This inherent uncertainty isn't limited to the quantum world. It permeates our everyday experiences, influencing everything from the weather to the stock market. Think about predicting the weather. Meteorologists use sophisticated models and vast amounts of data to forecast the weather, but they can only predict with a certain degree of probability. Even with the best technology, there's always an element of uncertainty. Small changes in initial conditions can lead to vastly different outcomes, a concept known as the butterfly effect. The future, like the position of an electron, remains shrouded in a veil of uncertainty. We can make educated guesses, but we can never be completely sure. This uncertainty is a fundamental part of life, challenging us to adapt and embrace the unknown. In the 1920s, German physicist Werner Heisenberg formulated his now famous principle, turning the world of physics on its head. He showed that uncertainty wasn't just a practical limitation, but a fundamental property of the quantum world. Before Heisenberg, physicists believed that with enough information and precise enough instruments, we could, in principle, know everything about a physical system. Heisenberg shattered this deterministic worldview. He demonstrated that there are fundamental limits to what we can know about the universe at the smallest scales. This wasn't a matter of technological limitations or experimental errors, it was a fundamental law of nature. Even with perfect instruments, we could never simultaneously know both the position and momentum of a particle with absolute certainty. Heisenberg's principle wasn't just a mathematical curiosity, it had profound philosophical implications. It meant that the universe wasn't a giant clockwork mechanism where everything was predetermined. Instead, it was a realm of inherent uncertainty, where chance and probability played a fundamental role. To understand why the uncertainty principle arises, we need to delve into the strange world of quantum mechanics, a realm where the rules of classical physics no longer apply. Here, particles like electrons don't just follow simple paths or trajectories. Instead, they exhibit behaviors that are both fascinating and perplexing. In this microscopic world, particles like electrons can behave like waves, spreading out and interfering with each other in ways that defy our everyday experiences. Conversely, waves can exhibit particle-like properties, appearing as discrete packets of energy under certain conditions. This wave-particle duality is one of the most mind-bending concepts in physics, but it's key to understanding Heisenberg's principle. It challenges our classical notions of particles and waves, forcing us to rethink the very nature of reality. Imagine a wave on the ocean. It moves and flows, spreading out over a vast area, never confined to a single point. This wave doesn't have a precise location. It's spread out over a certain distance, much like how an electron's position is described in quantum mechanics. Now, imagine trying to confine that wave to a small region. You might be able to squeeze it down, but in doing so, you'd alter its properties. By confining the wave, you increase its uncertainty in momentum. Its tendency to move in a particular direction becomes more unpredictable. The same principle applies to particles in the quantum world. When we try to pin down the position of an electron, we're essentially trying to confine its wave-like nature. But confining the wave makes its momentum more uncertain. The more precisely we know the position, the less precisely we can know the momentum. And vice versa, if we try to precisely measure an electron's momentum, its position becomes more spread out and uncertain. This trade-off is at the heart of the uncertainty principle. This isn't just an analogy. It's a direct consequence of the mathematical formalism of quantum mechanics. The equations that govern the behavior of particles are fundamentally wave equations. These wave equations describe how particles propagate and interact, and from them, the uncertainty principle naturally emerges. It's a built-in feature of the quantum world. The equations that describe the behavior of particles are wave equations, and they inherently include the uncertainty principle as a fundamental aspect of their structure. Thus, the uncertainty principle isn't just a quirky side effect. It's a profound insight into the nature of reality, revealing the deep connection between waves and particles in the quantum realm. Heisenberg's uncertainty principle forces us to abandon the classical deterministic view of the universe. This principle, formulated by Werner Heisenberg in 1927, states that it is impossible to simultaneously know the exact position and momentum of a particle. The more precisely we know one, the less precisely we can know the other. This inherent uncertainty is not due to any flaws in our measurement tools, but rather a fundamental property of nature itself. And embrace a new picture of reality, one where chance and probability reign supreme. In this quantum realm, particles are described by wave functions, which provide a probability distribution of where a particle might be found. These wave functions can interfere and overlap, creating complex patterns of probability that defy our classical intuitions. In the quantum world, particles don't follow well-defined paths like billiard balls on a table. Instead of having a single trajectory, a particle's path is a superposition of all possible paths it could take. This concept, known as quantum superposition, means that until we observe a particle, it exists in multiple states simultaneously. Instead, they exist in a haze of probability, their properties smeared out until a measurement is made. When we do measure a particle, the wave function collapses, and the particle chooses a definite state. This collapse is instantaneous and non-local, meaning it happens everywhere at once, a phenomenon that puzzled even Einstein. This doesn't mean that the universe is random or chaotic. The underlying laws of quantum mechanics are precise and mathematically rigorous. They govern the behavior of particles with exacting detail, but in a statistical manner rather than a deterministic one. The laws of quantum mechanics are still deterministic in a statistical sense. They allow us to calculate the probabilities of different outcomes with great accuracy. For instance, we can predict the likelihood of finding an electron in a particular region around an atom, even if we can't pinpoint its exact location at any given moment. They allow us to calculate the probabilities of different outcomes, even if we can't predict any single event with certainty. This probabilistic nature of quantum mechanics has profound implications for our understanding of reality. It suggests that at a fundamental level, nature is governed by probabilities rather than certainties. This probabilistic view of reality might seem strange and counterintuitive, but it has been confirmed by countless experiments. From the double-slit experiment to quantum entanglement, these phenomena have been observed and verified repeatedly, leaving little doubt about the validity of quantum mechanics. It's one of the most well-tested theories in all of science. The predictions made by quantum mechanics have been confirmed to an extraordinary degree of precision, making it one of the cornerstones of modern physics. This shift from a deterministic to a probabilistic view of reality has profound philosophical implications. It challenges our traditional notions of causality and determinism, suggesting that the universe is not a clockwork mechanism but a dynamic interplay of possibilities. It challenges our notions of cause and effect, of free will and determinism. If the future is not predetermined, then our actions might not be bound by a strict causal chain, opening up new debates about the nature of free will and human agency. It suggests that the universe is fundamentally uncertain, that the future is not preordained but rather a tapestry of possibilities. This new picture of reality invites us to rethink our place in the cosmos and the very nature of existence itself.